Perhaps you'll remember that in a previous video, we looked at the idea that if 3 points are on the same line, we can determine that they are on the same line by, I'll give these points coordinates. By setting up a matrix where the third component in each row is a 1, and if the determinant of this matrix equals 0, then the points are collinear. Points are collinear. And we did that in a previous video when we did an example. In this video, we're going to look at the idea of points being coplanar. That is to say, when points are on the same line, we call them colinear. If points are on the same plane, we call them coplanar. Something to keep in mind here is that any 2 points, let me just put 2 points down here, those have to be on the same line because you can draw a line through any 2 points. I did a terrible job there. Hope you get what I'm trying to say. Take 3 points though, and they may not be on the same line. Any 2 points are on the same line, but any 3 points may not be. Any 3 points, however, are coplanar. In other words, if I draw 3 points, even if they're not on the same line, they go through the same plane. This is really hard to demonstrate in 2 dimensions. I could try and draw it in 3 dimensions. We'll see how that goes. I have a set of X, Y, Z axes here, and if I draw a plane floating in space, then 3 points, no matter where they are floating in space, will go through a plane. They may not go through that plane, but they go through a plane. Normally you draw the points first and then draw the plane that goes with it, but I can't draw, so this is the best I can do. So any 3 points floating in space will have a plane that goes through them. But will 4 points be on the same plane? And it's the way we're going to determine that is the same way as we did that, determine whether 3 points in R2 were on the same line. So this is our R2 example. And we're now going to talk about in R3, points in R4 have 3 components, an X, a Y, and a Z, because, for example, any single point will have an X, a distance you have to go out X, a distance you have to go over Y, and a distance you have to go up Z to get to that point from the origin. Okay, so coordinates are X, Y, and Z. I'm going to check for 4 of these whether they are coplanar. So I have X3, Y3, Z3, X4, Y4, Z4, 5, and 6. And I want to know if those 4 points are coplanar. And we're going to do that exactly the same way. We're going to set up a matrix. We're going to add a column of 1s. We're going to call that matrix, I don't know, F, I guess. And we're going to say that if the determinant of F equals 0, then the points are coplanar. So it's exactly the same as we did in R2, but with, first of all, an extra dimension and second of all, an extra point. So that's the theory behind this. Let's do an example. We'll go to the next screen and I'll do an actual example of this for you. Okay, here's an example, and I've written this one in a little bit of a different way because I think it's important for us to be able to take a situation and kind of analyze it and put it into terms that we know we can deal with. So the question here is, does the point containing these 3 points, 1, 0, 2, 1, 1, 1, and 2, 0, 1, those 3 points will be on the same plane for a plane somewhere. But does that plane go through the origin? And the origin is the point 0, 0, 0. So in a way, in kind of a sideways way, what we're asking here is, are these 4 points on the same plane? We know these 3 are, but is this point on that plane also? And so in order to determine this, what we're going to do is set up this matrix. And we're going to put 1s in our 4th column. What we want to do now is I'll say we give that a name, is to find the determinant of A. And if that equals 0, then the answer will be yes, these points are coplanar, and that means that our origin is one of the points, all 4 points goes, all 4 points are on the same plane, and yes, the origin is also on the plane, therefore the plane goes through the origin. Okay, so what we need to do now is figure out what the determinant of A is. And the good news is, because the origin is one of our points, we've got this row here that has almost nothing in it but zeros. So I'm going to use that one to do my cofactor expansion to find the determinant of this matrix. So I'm going to have 0 times a submatrix, 0 times the determinant of a submatrix, plus 0 times the determinant of a submatrix, plus 0 times the determinant of a submatrix, plus 1 times the determinant of a submatrix. And I'll highlight that here. I'm going to get that submatrix by crossing out the row that the coefficient is in and the column that the coefficient is in. And I'm left with this submatrix here, and I want the determinant of that submatrix. And that's a 3 by 3 matrix, and I've got a couple of rows here that have zeros in them. And in fact, if I go by the column, then I've got 2 zeros in that column and only 1 1. So that'll be the easiest way to figure out what the determinant of that submatrix is. So let me do this. 1 times the determinant of, in fact, I'm going to write it as an actual determinant. So the determinant of this matrix, 1, 1, 1, 2, 0, 1. Okay, so now I have to do that work, and I'll go ahead and highlight the row or the column rather, that I'm going to use for my coefficients, and I get to start this process all over again. The determinant of A is equivalent to, because of all these zeros, 1 times the determinant of this submatrix here, and that is equal to 1 times, I won't write the 1 times, 0, where's my pointer? There it is, 0 times a determinant of a submatrix, plus 1 times the determinant of a submatrix, and we'll come back and figure that one out, plus 0 times the determinant of a submatrix. So we really, again, only need to figure out what the submatrix is for this entry here and find that determinant. All right, so let me get my highlighter and I will highlight the submatrix. First of all, I'll highlight the rows and the columns. I'm looking for that 1, so I'm going to cross out the row and the column that the 1 is in, and I'm going to make the determinant that's left is coming then from these entries. Right? The matrix of the entries that are left is the matrix 1, 2, 2, 1. And that, I don't need to write the 1 times anymore, but I can write this 1 times 1 minus 2 times 2, and that's -3. So what I've done here is I've taken a 4 by 4 matrix and I've used clever choice of a row to make it really easy to find the determinant of the 4 by 4, turning that into the determinant of a 3 by 3, and then again very carefully choosing the column that I want to use for my coefficients to make the the computations. I only have one determinant to find in each case because all the other entries are zeros. But what I found in the process of doing that is that the determinant of this is not zero. The determinant of the 4x4 matrix I've been working with is not zero. And therefore, I can say that the plane containing these 3 points does not also contain this point. So these 4 points are not coplanar. And therefore, the plane containing these 3 points does not go through the origin. Now, again, back in when we were talking about the case in R2, when we only knew how to deal with up to a 3x3 matrix or find the determinant for a 3x3 matrix, we said that if we had 2 points, I'll call them x1, y1, and x2, y2. If we put those into a matrix, x1, y1, x2, y2, we added a generic point xy, and we included our column of ones, that if we set this determinant equal to 0, the determinant of this matrix, the determinant of that matrix right there, we set that equal to 0, that would produce the equation of the line through these 2 points, through the 2 points that we've been given to start with. So let me write that out, the equation of the line. In R3, that's in R2, in R3 we have something very similar. If I'm given 3 points, and I think I'll call them x1, y1, and z1, that one there is a comma, x2, y2, z2, and x3, y3, z3, and we put those into a matrix. We add a generic 3-dimensional point up here at the top. We include a column of ones. We take the determinant of that matrix, set it equal to 0, we will have the equation of the plane that those 3 points go through. Now on the previous screen I had 4 points. Here I only have 3. I have added a generic XYZ, X1, Y1, and Z1, X2, Y2, and Z2, and X3, Y3, and Z3 are all specific values. We just don't necessarily know what they are, right? These are all specific numerical values. They're all numbers. I forgot to put my 3 on my R3 there. X, Y, and Z are not. These are variables. So once we've done this work, we'll still have an X, Y, and Z. These would, in a real example, these would actually be numbers, and these will be X, Y, and Z. These will be variables, and we'll have then an X, a Y, and a Z in the final form of our work. Okay, so that's all I'm going to do on the theory for this one, but on the next screen, I'll do an example of how this actually works. Okay, here's an example of a problem like that, and I'll be honest, I've cheated and given us some really easy points to work with in terms of finding the determinant of the resulting matrix. These are the points where x equals 1, but y and z are both 0, y equals 1, but x and z are both 0, and z equals 1, but x and y are both 0. We could connect these points and get a sense of what the plane would look like in the first octant. All right, now obviously the plane is bigger than that, but if this was a room with solid walls and we couldn't see the rest of the plane, the part that we would be able to see is what you can see in the diagram here. So this plane is kind of floating in the corner of the room like this. And what we want to know is, what is the equation of that plane? And there are other techniques that we can use to find that equation. In particular, we took a look at that in I think it was the first unit of the course, where we just learned how to write the equation of a plane if we knew 3 lines. But we can use the idea of a matrix and a determinant to do that as well. So let's do that now. We're going to set up the matrix that contains the 3 points. We're going to include, let me do this. I didn't really give myself enough room. We're going to include a generic XYZ at the top of that. And we're going to augment it with a column of ones. And what we're going to do, I should have left the bracket off and just done determinant bars, vertical bars for determinant. We want to set that equal to 0 and see what happens. So now I actually need to compute the determinant of this matrix. The determinant it's already a determinant because I've used vertical bars here to indicate the determinant. The matrix is made up of the entries that you see inside it here. And I want to make it as easy for myself as possible. So I can do this a number of different ways, but I've noticed that every single row has at least 2 non-zero entries in it, right? And in fact, they all have 2 non-zero entries except for this one here. And the good news is that those non-zero entries are 1, so we don't have to worry about multiplying, scaling by anything. And so I could either choose one of these 3 rows, or I could use one of these 3 columns. And I think I could also use column 4. I mean, there's nothing wrong with that, but I'll have 4 subdeterminants to compute. And if I do use a row, I'll only have 2. So I'm going to go ahead and use, let's see, I think I'll use this one here. I'm going to use row 2 for my coefficients. So that means I'm going to need to solve this equation. I'm going to need to write out the determinant of this 4 by 4 matrix, which is 1 times a subdeterminant plus 0 times a subdeterminant plus 0 times a subdeterminant plus 1 times a subdeterminant. And in fact, once again, I'm actually going to write the determinant right in there. I'm going to have a 3 by 3 determinant here and a 3 by 3 determinant here. Okay, let's see. So for my first one, what is left when I cross out row 2 and column 1 is the determinant is the matrix made up of the entries that I'm going to highlight in yellow here. Okay, so that matrix is YZ1 1 0 1 0 1 1. And in blue, I'll start by crossing. Well, how do I want to do this? I guess I'll start by crossing out. Maybe I'll do this in an actual pen. I'm going to cross out the rows, row 2 and column 4. And I've done that in pen instead of highlighter. And now I'll use a highlighter in a different color. Let's see, I'll go with pink to indicate the values I want to include in my other subdeterminant here. So I've got X, Y, Z, 0, 1, 0, and 0, 0, 1. So that's all I need to do because the other entries here would have produced a 0 times a subdeterminant, and that would be 0. Okay, this one looks like it's going to be pretty easy to me because I've already noticed as I wrote this out that one of my rows has nothing in it but a single 1. I mean, has zeros in it except for the one non-zero value, which is 1. So that's going to be an easy one to work with. In my first subdeterminant, I have 2 rows that have 2 1s and 1 0. So it doesn't really matter which one of those I use. Either way, I'm going to have to compute 2 subdeterminants for this term here. And I'll have to compute 1 subdeterminant for this one. And the reason I know that is because I've only got 1 non-zero entry in this row, and I have 2 non-zero entries in this row. So let's get started with this one. I want to use for this one here for my first one, I'm going to use this row. I could have used row 2 instead, but I'm going to use this row. And I only need to compute 2. I don't need to compute this one here because of the 0. So I need to compute the minor and cofactor for this term, for this entry, and the one for this entry. So let's see, how do I want to go about doing this? I think I'll stick with white. And I don't need to write down this 1 anymore. In fact, let me erase it from, no, I think I'll leave it there, but I don't need to write it down anymore because it's just a scalar of 1. It doesn't change anything. So I'm going to start with row 3, column 2, and I'll write out the cofactor there. I'll start with the number, the coefficient, which is 1, and I'm going to multiply that by the determinant of the things that are the matrix that's left over when you cross those out. That's y1, 1, 1. I'm looking at not these values and not these values. That leaves these values. Okay, and the sign of that determinant, the sign of that cofactor, is determined by the position of the value I got this coefficient from. So just as a reminder, this 1 here is coming from this position here. I could say times 1 if I wanted to include that 1 there, and I don't think that's necessary, which is why I left it off, but I just want to be clear. These values are not always 1, so it's important to know where they're coming from. Okay, let's see, how far did I get here? I have a y1, 1, 1 matrix, and I'm taking its determinant. This value is coming from here. This value is coming from here. I need to know the sign of this term. This is coming from row 3, column 2. 3 plus 2 is 5. So I'm going to take -1 to the 5 power, and that's negative. So for this term, I'm going to have negative whatever this determinant is. Then I'm going to add -1 to some power. I'll come back and figure out what that power is. 1 times, that 1 is now coming from here. So that's, again, I'll do the same thing as I did before. Like I said, it's not strictly speaking necessary. Let's take this 1 and write it down here. And let's take this 1 and write it down here. And then I'll be left with the determinant of, I still have to go back and find this power. The determinant that's left over, when I cross out the row and column that 1 came from, and what's left over when I do that is yz10. Let's go back and figure out our sign. This 1 came from row 3, column 3. 3 plus 3 is 6. So that becomes a 6, and that is an even number, and their -1 to an even power is always positive. So I'm going to have then plus 1 times this determinant. Okay, so what I have done here so far, I'm going to brought this 1 down here, and this 1 came from here. All I've done so far is what you see in this determinant. I have not yet dealt with this one. So let's do that next. I'm going to add to that -1 to a power times this 1 times this 1, that's my coefficient, and I'll get my subdeterminant by crossing out row 3 and, row 3 and column 3. Row 3, column 3 plus 3 is 6, so that's -1 to an even power, so that's going to be positive. 1 times, where's my determinant? I have xy01. So xy01. And I only had one term to do for that piece of my problem because I only had one non-zero entry in the row that I chose to use for my cofactor expansion. All right, now I've left something off here and it's really quite important. So I'm going to add it back in here and make the comment that this whole thing is contingent upon the determinant of this equaling 0, and I've left off the equals 0 at every stage here. Not intentionally, it was a little bit careless of me, but the fact that I've noticed it means that I had an opportunity to come back and remind you that is a very important piece of this equation. Literally, it's not an equation without it. I mean, we're solving an equation here, so we need that piece to be there. All right, let's go figure out what these determinants are. This implies that the first determinant that I have here is y times 1 minus 1 times 1. And I'm going to add to that the determinant y times 0 minus z times 1. I'm going to add to that the determinant x times 1 minus y times 0. And that's still equal to 0. And I see that I said y times 0, but I wrote y instead of 0 there. So let me correct that. So now I have this equation. I'm going to distribute and simplify. I have negative y plus 1 minus z plus x equals 0, or x minus y minus z equals negative 1. Now, if you look this up in a calculus textbook or work with different rows or columns for your cofactor expansion, you may actually get a different answer. But the equation of a line in R3 is not unique. So I would argue that your answer and my answer can both be correct, even if they're different. So this is just an interesting application in how one of the ways we can use determinants. And now that we know how to take determinants of much larger matrices, we can use them for much larger spaces. If and or when you take calculus 4, vector calculus, you'll learn that there are other ways. Actually, at Whatcom, it's done in calculus 3. We do our equations of lines in planes in space in calculus 3, because we do things a little weird here. But when you take that course, you'll find that there are other ways to come up with the equation of a line in space or an equation of a plane given 3 points in space. But this is a nice alternative, and I would argue that you can use either technique, although in your calculus class, I would encourage you to use the calculus that you're being taught there, because that's what you're trying to learn. So it's an interesting application. I'm not going to highlight it heavily on quizzes, but I think this is an interesting thing to be able to use and to compare to the situation we had, the very similar situation we had in R2.